Hello everyone, today I want to talk about our work, CARIN, which stands for Wireless CSI-based Driver Activity Recognition and the Interference of Passengers. As we know, the CSI-based Wi-Fi sensing is a very popular choice in many application areas and is a very hot research field. For example, for the in-room applications, it can be used for fall detection, breath and heart rate tracking, and even interactive gaming. And for in-car active scenarios, it can be used for driver behavior recognition, fatigue detection, etc. But there is a large limitation for the Wi-Fi-based sensing work, which is a multi-people scenario. When there's many people in the same environment and they perform activity together, it may disturb the CSI pattern and make a mismatch between the observed CSI signal pattern and the learned CSI pattern stored in the classifier. After that, it will make the misclassification and further reduce the recognition performance for such system. So in this work, we propose CARIN, which can recognize driver activity for the in-car scenario and the interference of passengers. So in CARIN, we leverage a combination-based solution which profiles all possible activities by using Cartesian product. For example, if you have 5 activity types predefined in the activity set, in CARIN it will profile it to a total of 25 activity combinations. Stand for every possible activity combinations. You may think that the combination-based solution is very trivial and brute force, but there are two major challenges. First one is synchronization issue, because not all activities start at the same time, and the time difference between two different activities can be any continuous number that will lead to infinite number of combinations. But for the in-car scenario, this problem is not very severe because the duration and the moving scale for in-car activities is rather small. But more important, the second challenge is the combination explosion. Because with the number of passengers increases, we need to profile all possible activity combinations. So the computation complexity will grow exponentially. So in CARIN, we need to design a combination reduction algorithm to solve this problem. To design this combination reduction algorithm, we made a key observation in CARIN, which is the CSI signal from two separate activities can be added together to simulate real-world activity combinations. For example, if you look at the first column, represent the driver-only activity, and the second column, which represent the passenger-only activity. If we add the two spectrum together, we can get a simulated activity combination. Shows in the third column, which is very similar to the real-world activity combination spectrum shown in the last column. Based on this observation, we can design our combination reduction algorithm. First step, we can calculate when we get online observed CSI signal, we can calculate the average Doppler shift for this observed CSI signal. After that, for every possible activity combinations, we can sum up the frequency shift for the single activities, which is stored in our offline database. After that, we can compare the online observed CSI signal to its average Doppler shift and the offline simulated Doppler shift by the single activities and calculate the distance between the two activity combinations. After that, we can eliminate those combinations with a distance larger than threshold. And in the classifier, we only load those unfiltered activity combinations and neglect those filtered out ones, so that in the classifier, the computation overhead can be reduced. So in our experiment, we use a real car, Toyota car, for experiment and establish one communication link inside the car. For target activities, we investigate 8 driver activities together with 7 front passenger activities and 3 backseat passenger activities in total for the experiment. In CARIN, we mainly compare CARIN with 3 baselines. The first one is WeMU, which is a state-of-the-art multi-people in room human activity recognition system, but it can only work for large-scale activities, mainly for in-room scenario. The second one and the third one are all proposed for the in-car scenarios, but not designed for the multi-people scenario. So it may perform poorly when there's a passenger inside the same car with the driver. So the results are shown here below in the 2 figures. The first one shows the recognition accuracy for CARIN is about 90% for the front passenger plus driver scenario. And the second figure shows the CARIN also successfully reduced the computation overhead by about 72%. So to conclude, in this talk, we'll talk about CARIN, which is a CSI-based recognition scheme under the interference of passengers. CARIN aims to solve the multi-people scenario issue for the in-car scenario for Wi-Fi-based sensing scheme, and it achieves an accuracy of 90.9% while reducing the computation overhead by 72%. That's all my talk. Thanks all for the attentions, and you may ask questions after this.